Hello everyone, my name is Marios. I'm a PhD student at the University of Edinburgh, and I'm really happy to present our recent work that we're doing with collaborators from here, but also from Max Planck Institute in Potsdam. So today I'm going to talk about clustering effects on gravitational waves, dark siren determination of the Hubble parameter, which is an ongoing work, and hopefully it's going to be on archive when we start the conference. The Hubble parameter, the Hubble constant, is a very significant, a very important cosmological parameter that parameterizes the expansion of the universe. In recent years, the measurement of the Hubble parameter has become quite intense. Increased measurements with increased accuracy between the early and the late universe seem to disagree. So we have the Planck and the CMB measurements that give a small value for H0, while the late time observations based on supernova, the key feeds and supernova, give a larger value. And if you take into account statistical errors, both measurements disagree with quite a significant level. And of course, we need to find if this is something that lies on systematics in the observations or it involves some new physics. And of course, there are a lot of different measurements and methods that try to measure H0 in order to resolve this tension. Of course, gravitational wave observation is one of them. So the logic is very similar to all the other methods. You need to find the distance and the velocity of the source, and the distance, it's quite easy from gravitational waves, since it comes directly from the gravitational wave signal, while the velocity, this creates a problem. So there are many methods that have been proposed of finding the redshift of a gravitational wave. However, this is not something that can be done really easily. Of course, the most direct approach is to find the source of the gravitational wave, observe it in with electromagnetic observations, and find the redshift through them. However, there are a number unfortunately, we only have one event. I'm going to come back into that. However, there are a number of different other methods, and today I'm going to talk mostly about two. Get the redshift in a statistical way by using a collection of galaxies in the gravitational wave localization volume. So first of all, what is a standard siren? So a standard siren is a gravitational wave observation which has where we have managed to observe an electromagnetic counterpart. So from that, we can get independent information, redshift information, and then use this to estimate a velocity, and through the Hubble manage to constrain the Hubble parameter. This has been done only once, but as you can see, of course, it can be competitive with our other techniques. Yes, so the next step is, unfortunately, because it's quite rare events and we only have one, is to use a different technique. So dark sirens observations, which are gravitational waves with now electromagnetic counterparts. So that means that we don't know exactly the source of the gravitational wave to manage to get some information about the Hubble parameter. And the way that we usually do that is use the sky localization of the gravitational wave in order to get some information about the possible hosts. So this is an example where it has been done about the standard siren, but now with dark sirens technique in Fishbach et al., where you can see you have a localization volume that includes a number of galaxies, where you have information about their redshift and luminosities, and based on that information, you can combine them in order to get a posterior on H0. And if you want, you can include more physical characteristics like the luminosities of the galaxies here in order to get to include some more physical weights in your final determination. But as you can see, compared to the counterpart one, it performs as expected much worse. And of course, it's not competitive with versus the case, even with many more events here after the second run of LIGO and Virgo. It's still, the results are not competitive. However, we expect to observe many more events without counterparts. So, for example, the majority of the binary black hole events are not expected to be able to see a counterpart. So combining them, however, we expect many more of these observations. So combining them, we hope to get a much more precise determination of H0. And this area of research is very active, both with observational and theoretical studies. And in this case, we want to investigate clustering effects by taking into account and using high-resolution numerical simulations. So in 5+1 steps, the procedure of what we want to do is to put an observer at the center of our simulation box. Then we're going to create mock gravitational wave observation by choosing a random halo, a random galaxy in our simulation, and calculate cut a cone based on the realistic sky localization errors, and take into account all the galaxies inside this cone that can contribute to the gravitational wave event. So the way that we create the cones is, in a way, we try to replicate the real gravitational wave observation by imposing two errors, one error in the opening angle of the cone, and one error based on the distance determination that gives you. And based on this, we take into account all the galaxies inside there. Now that we have created this cone, we want to find, as a first step, we want to find which is going to be our true gravitational wave host. And the way to do that is to include information about the position of the galaxies inside this inside this cone. So we use a number of weights depending on the angular position of the cone. So this is an example of a 2D projected distribution for the galaxies inside one cone. You can see here with the star where we, at the end, we put the true gravitational wave source. And we include the weights so that if you are closer to the localization region, you have a higher probability of hosting the gravitational wave. And at the same time, we include weights that depends on the distance from the center of the cone, which is expected to be the peak of our distance information from the gravitational wave event. And this is at the same example where the gravitational wave is compared to the center. This is the distance between observer and the center of the cone. So we follow a similar procedure for all the cones in the simulation, and we also consider some selection effects due to the cone geometry. And the next step is what we expect now to gain from the numerical simulation is the clustering information. So instead of using a uniform distribution, which is the green dots here, that was used in previous studies, we want to have extra information based on the clustering of the simulation. An example here are the blue dots, where the intuition behind the improvement of this method is that clustering is going to give you a high probability of the true host sharing the same distance and same information with other galaxies, and as a result enhancing the dark sirens technique. Finally, the power of this method, of course, lies in the statistics. However, by combining many such cones that are cut from the simulation. You expect to build statistics and more or less this to contribute to the one true value for the Hubble parameter. Then as a sanity check, as a base model, we also use a uniform box. So in order to estimate the improvement of our method based on clustering. So in our simulation, we recreate, we produce a similar box where it has the same number of galaxies, but now uniformly distributed. And then we use this as a base model to compare the improvement of the clustering versus the uniform case. As a first result, we performed a very basic H-node stacking. So we take for each galaxy inside all the cones, its H-node value based on its distance from the observer, and we just stack all together in one histogram in principle improving from the work that MacLeod and Hogan have done in 2008. And here you can see, even with this simple method, you can see the improvement of the clustering information compared to a uniform box, which is about 5% in this in that case, where the solid line give you the result of a uniform distribution of galaxies, and the blue dashed line give you the result of a clustered distribution. And it can be seen here from the quantiles that the red ones that are related to the cluster distribution are much more precise compared to the uniform one. As a next step, we can increase our methodology by including specific weights on the galaxies inside the cone based on their position, single posteriors, and then combining all the posteriors together for all the cones. And then we end up with some Gaussian results for the H-naught. And here is an example of how our posteriors improve with the increased number of events. And this is the case for the clustered. As a next step, what is quite important to check is completeness issues. So surveys, we know that they have some observational limitation and can observe all the galaxies. In many cases, in the region they observe. So when we have a gravitational wave observation, we try to find the galaxies inside its sky localization region. Some of the galaxies can be missing due to the survey's limitation. So already in grade 9 2020, in a nice study, have checked that more complete catalogues are expected to give better results. But this was using a uniform galaxy configuration. So in our case, we want to check if clustering can also help in this case, even though we don't know all the galaxies in the region and we have to uniformly put them back. Some clustering information is retained from the original galaxies that are inside the region. This is so far a work in progress, but we already see here the main results. We have three different cases. The red ones are the results from a uniform box, where all the galaxies are uniformly distributed. The blue one is from a clustered box, where we have a perfect knowledge of all the galaxies in the region. And the orange one is from 85% complete catalog, with the rest of the galaxies are missing due to observational magnitude limitations. So we complete the missing galaxy by uniformly putting them in the region. Some extra information on that I have included in the bonus slides at the end. But the main takeaway message from here is that, okay, all the methods seem to perform well, so they converge to the input value. But here in the statistics of the errors of the final H0 posteriors, we see that first of all, as expected, the complete catalog is performing better than all of them, and better than the uniform one. So the clustering has important implications, but also even an incomplete catalog that is completed then uniformly can perform is performing better than its uniform counterpart. So clustering can help in the convergence and to reduce the scattering of the final result, even if some galaxies are missing. So to sum up, in our case, we have shown that Dark can provide a robust method for calculating the Hubble parameter. We showed and tried to quantify how much the power of the clustering technique, and we found that the convergence is faster compared to the uniform case, with resulting an improvement of about 2%. And the clustering introduces less scattering and better convergence in complete catalogues. So thank you very much. I'm including in the slides some bonus slides for extra details of what I've talked, and I'll be happy to talk more about that in the conference.